Welcome to our Support Vectors weekly paper reading. Today's paper topic is Drowning in Documents, Consequences of Scaling Reranker Inference. It is a very interesting paper that came out a couple of months ago in November. And I found this interesting because it goes to the heart of some things we do in one of the dominant use cases of AI, namely retrieval augmented generation and in semantic search. When we do semantic search, most of us, what we do is we take a two-tiered approach. We used vector search to first get candidates, search result candidates against a query, and then we use a re-ranker to improve upon the quality of the results, to improve that. So therefore, while this has been pretty much a de facto approach, well-established approach, these folks, and these are obviously well-known guys, Matai Zaharia, Omar Khattab, and the rest of them, and they have come out, and partly from Databricks and partly from my alma mater, University of Illinois, Urbana-Champaign. What they observed is something remarkable. They show in this paper that if you give the re-ranker too many documents to re-rank, it actually starts underperforming. It is not something that people would have expected. We all, with the standard understanding of transformers, we all believe that re-rankers, to the extent that it uses cross-attention between the query and a document directly, it would always yield superior results. So to see empirically that that is not the case, when you are comparing a query against a lot of documents, actually your recall at 10, that is the top 10 document, top 10 results, takes, after rising up to a certain limit, it begins to precipitously fall or decline. It is not something you would have expected. This paper goes into why possibly it is happening. They have a few hypotheses. We will have a few hypotheses of our own, but it's a very simple, short paper. Nevertheless, it is a cautionary tale because all of us are using re-rankers. All of us are using vector search. So the way I would go through this paper is first explain the main idea that they are, give you the background to understand the main idea, and then in the second iteration, then we'll quickly walk through this paper. Right? So with that understanding, let me just give you the background. The background of this, the things that we will talk about are these. We'll talk about the retriever. Oops, sorry, this is pretty fat. Retrievers. The retrievers come under two types. They are the so-called BM25. Think of your BM25 is an algorithm that basically is TF-IDF based sparse search improved upon significantly. It is the foundation of projects like Elasticsearch and so on and so forth. The traditional keyword search, think of it as simple keyword search. Sparse search. It is, or another word is inverted index plus bag of words, vector search, things like that. These are the common words differently used for search engines that use essentially the BM25 idea. Think Elasticsearch, Solr, OpenSearch, so on and so forth. Right? Or if you're using Python, you can of course just directly get the project, the library, BM25 library, and start using it. So this is it. Then you have the so-called, so these are often called sparse. So these are sparse search. Then you have the so-called dense search, semantic search, AI search, etc. The basic idea in all of these is you take a document, every document DI is mapped. You have a mapping function for DI that converts it into a vector I, embedding vector EI. This is true for the dense search. Now, when you do this embedding vector, this kind of a mapping function, we use For dense search or the AI search, we use a transformer. In particular, the encoder, it was much more common to use the encoder mostly. So for example, you would use bird star, any one of the bird families. Right? And what you do is you train the encoder to use a form of contrastive loss or one of its cousins. And cousins. The way you would do that is, the simplest way that you would do that is, you would take two documents in supervised learning, which you know are similar. So for example, you would take a document, let me call this XI, and you would take a document that is similar to XI, you know is similar to XI, right? And there are two ways. The original way was triplet loss, though later on we moved away from it, triplet loss, and then you would take a document that is truly random or different. This would be the triplet. These two are similar. These two, to the extent that it is a random document, a random sentence, you assume that it is dissimilar. Dissimilar. And then what you do is you try to maximize the similarity between xi and si using some sort of a distance function or similarity function, and minimize the similarity between xi and the ri. Right? What you pick a particular thing, and what you do is actually, no, I take it back. Ex, the embedding of xi, the embedding vector of the similar matrix, similar I, and the embedding vector and the embedding vector of these two. So you train the encoder such that when x goes to ex, right, and similar goes to es and random goes to er, these two in a vector space, ex, es, they land proximal to each other, and you want to make sure that er ideally falls really far off in the so-called embedding space. You can do it like this. Now, there are multiple ways that people do it. There are many subtleties to the contrastive loss functions. You can do it using cosine similarity. You can do it using distance similarity. You can do it using triplet loss, or what is much more common these days is to use a different approach. Nowadays, much more common to just have training data like this. And what you do is, suppose you take a mini batch that you're passing through the transformer, then you would end up with, let's say, x1, s1, x2, s2, x3, s3, all the way to sn, xn. The way you create a de facto, the triplets, is you basically say, let's take this whole thing and we will create a loss. We will look at the dot product. Let's say you look at the dot product of these two, right? And the xi, the vector produced from xi and similar I, these two vectors, the dot product, whatever it is, let me just call it dot product di, ii. This is a dot product between the vector and its similar vector, right? And then what you do is you look at something else. You go with the assumption that Sj, where I is not equal to j. In other words, you look at you artificially create these on the run from the mini batch Sj, where I not equal to j. So you assume that these two will not be similar, isn't it? Does that make sense? The first sentence may be about dogs. The second sentence may be about hammer. The second pair may be about hammers, right? So obviously, if you create or take a sentence about dog and a sentence about hammer, you do expect that they should be pretty divergent, and the similarity between them should be very low, right? And so what you do is dij, you want it to have it small. You want this to have large, compared to this. And so what you do is you create a loss function that basically, and obviously because cosine can take values from -1 to 1, one easy way to enforce that it takes values in the 0 to 1 range, you exponentiate it, dii, and summation dii plus summation I not equal to j over dij, all of these exponentiated. If you do that, you end up with a ratio, right? You will end up with a ratio. And if you look at this ratio, this is your classic softmax. So it is quite common these days to use this a little bit more complicated loss function, because you have the advantage that you're saying, and this is something interesting, you're saying not only compare and make sure that the distance of x to similar is closer and far from the irrelevant one, but it is the similar item is closer than every irrelevant item. Do you see that? It's more a list wise, in some sense, a way of enforcing in the encoder that amongst all of the sentences, the actual similar sentence, the known similar sentence, should be closer in the vector space than anything else. So it's a bit more robust algorithm, and there's evidence that it works. So most of the new things are variations on this. So that is the theory of the retrievers. We are all familiar with retrievers. We all go to, for example, the MTab leaderboard on Hugging Face, and we find which is the best encoder these days, sentence encoder, right? Which gives you the best performance and so on and so forth. So we pick, right? We do tend to pick what we like, right? And there are quite a few in the open source and in the closed commercial world. There are quite a few encoders that are available. Now, then there are rerankers. Rerankers are truly, think of a standard BERT architecture. If you remember, the BERT architecture would take sentence S1 and sentence S2. And when you pass it through this, and you have a CLS token, etc., you can basically feed it into a classifier to produce the probability associated with S1 and S2. And based on how you design the loss function, you can, for the purposes of reranker, you can train a BERT encoder, BERT-like encoder, to give you, maximize the probability of S1, S2 when S1, S2 are similar and minimum otherwise, when they're dissimilar to be minimum, right? So this is your re-ranker thinking. What you do is you typically re-rankers are created by taking a trained BERT, a BERT-like, you can take BERT, Robert, this, that, distill BERT, whatnot. And after that, going through fine-tuning it with a data set like this. Now, there is a somewhat interesting asymmetry. The asymmetry that comes in is that to do vector similarity is cheap because you're dealing with cosines, right? You can take documents, a million documents, and in one-time effort, you can convert them all into vectors, right? Now you can, it's a one-time effort to create them into vectors, all of them. And then after that, you can do your loss functions and so on and so forth, and you can be easily training the encoder, the sentence encoder or the vector maker, right, retriever. On the other hand, re-rankers are a little bit harder to train, more expensive to train, because guess what? Because you're not comparing or doing a loss function on the vectors. You're doing a loss function directly on this text itself. You're directly comparing two pieces of text, sentence one and sentence two, right? And as it goes through, you're having a loss function directly on this probability. It is computationally more expensive, right? So typically what happens is this asymmetry shows up in that when you go back and look at how people have trained the sentence encoders for retrieval and the re-rankers, The re-rankers are usually trained with far less data because for the same compute budget, you can pass only a couple of orders of magnitude lesser data through the system, right? So that is something that we should bear in mind. Now, if you rewind back to 2018, when the transformers came out, people realized or they felt that given a user search, let me a search query, and suppose you have a document D1 to Dn in your corpus, you want to find out which documents are best search results. You can compare it to all of them. Now you realize that a direct query to document comparison is brutally expensive because you're literally using the full transformer every single time you're passing a Q query versus every document to produce the probability of the document being similar given the query. And then you're sorting through it and picking the top end. Nevertheless, the history of our field has been that people saw the potential of this. Today we call it re-ranker. People saw the potential of this. Google saw the potential of this and Microsoft saw the potential of this, and they went ahead with it nevertheless, despite it being more expensive. Till the first sentence BERT paper came out, which also came out in 2018 itself, pretty soon after BERT. And what the paper said is that, no, don't do that. Instead, go this two-step approach to EQ, create a vector embedding for the query, create a vector embedding for the document, DI. These are one-time efforts. These have been pre-computed. And now, when you have a query, just do dot product of it with DI. The reason you do dot products are multiple. First, dot products are a lot cheaper. Ever since numerical computing has come about, dot products have been the workhorse of the industry. The second thing is dot products we can do very, very efficiently because there's a whole technology that has been maturing of approximate nearest neighbor search. Most of you are familiar with FAST, perhaps, if you have been in this industry. If you're not, just think that you can find the nearest matches, the highest similar dot product items, or without necessarily doing order and computation is not needed. You can do it in a sublinear time frame. You can do it extremely efficiently. There are various quantization techniques, clustering-based quantization, hierarchical navigable small worlds map, and so on and so forth. And there are industrial strength implementations like FAST, which make it very, very easy for you to incorporate and do it at rapid scale. We are talking, and of course, today the social media companies, they all use this to do image search, text search, multimodal search, and they are doing it at scale between vector search, finding the top K nearest neighbors. They are doing this search across, while they are taking in vast traffic in parallel, user traffic in parallel, and they are still doing it within 20, 30 millisecond budget while they're handling thousands of requests at the same time concurrently, right? So it just speaks to the utter scalability and performance of the vector search methods. They're very, very mature. On the other hand, re-rankers are expensive. So the industry decided that the right way to do it and to have the best of both the worlds is this. What you do is, given a query to a query queue, what you do is you take your documents. Let's say that you have documents D1 to Dn, where n is equal to, let's say, 1 million documents. You take all of these and you pass it through an encoder, sentence encoder, text encoder, to produce the embeddings E1 to En, and you store those embeddings in your vector database. Then what you do is you take the query and you create the EQ, and now your EQ, you find K nearest neighbors. So this is the first, what this paper calls the retrieval step. In the retrieval step, you will get that. So you will get some, what comes out of it, therefore, is you have this search engine and query goes in. At the end of it, what comes out are, now these vectors, you remember which documents they pertain to. You will get the top K documents, right? If you want to make sure that your recall is high, just get more documents, right? Make sure that the K is a bigger number. Let's say it is 100 or 200 or something like that. Then suppose you want to do, you know that you have compromised because you're doing vector search. It's an indirect approach. You took a vector, you didn't do a direct string to string comparison. You instead did vector comparison. The implicit assumption is that you lost something along the way. It's an indirect comparison. So what you would do is you would take the top K results. Now K, let us say, is 100. Considering that you have a million before, getting 100 is a small number. And then you do refinement by comparing Q against each of the DI belonging to the top K. You would do a direct, full-blown cross attention or cross encoder uh, uh, thing where Q and DI goes in and you produce the probability of their similarity, like a full transformer kind of approach you would do. Full encoder, in which text, two sentences go in, two text goes in, and you're looking at the similarity between the two. When you do that, this is called the re-ranking. And one way to think about re-ranking is if you take sufficiently large number of results in the top K, if K is sufficiently large, then you can take care of the recall part. You'll have a pretty good recall. If your query, all the documents that potentially match your query will come up. Some will be more relevant than others. And re-ranking in a way improves the precision, because out of the 100, suppose you keep only 10, you want to make sure that your recall coming out of the re-ranker is better than what went in the initial 10 out of the 100 that you retrieved, right? The re-ranker improves that. So that is the basic idea that we have all internalized. Now, performance perspective, this is practical. Why? Because vector searches are very fast, but followed by this expensive search, expensive re-ranking, but you're re-ranking only against 100 documents, isn't it? 100 is a drop in the ocean. Actually, the numbers that most social media company have is not 1 million, but they are somewhere in the order of 100 billion or something like that, right? So when you think 100 billion versus just 100 documents to re-rank, you would agree that one is impossible, the other is practical. And that is how all of these semantic search architectures are made. They always use first retriever followed by a re-ranker, and then they move forward. And of course, this kind of searches are the foundation of RAG. One other thing it opens to you is the possibility that you can have a query pan out to multiple search engines, each of them emitting their results, and you pool them, you create a pool, then you send it to the re-ranker, pool of candidates, candidate results, and then you go to the re-ranker and then you pick the top 10, right? So let's say that each of these search engines, and it could have been vector search, it could have been Elasticsearch, it could have been different data, for example, one about marketing, one about finance, etc. And nevertheless, your re-ranker then takes care of putting it in the right order. So that was the classic theory, and that's how RAG and all these things are implemented these days. Modern production deployments are like that. Now, what this paper says is actually, with that as a background, you would agree that first there is a fundamental trade-off. If you want to increase your recall from the retrievers, what do you want to do? You want to increase the number of documents they produce. Then they won't miss. So imagine they use the word the goal set. Like, you know that for this query, these are the documents that must show up in the result. What is the likelihood that you would hit a near perfect retrieval of the goal set? Just increase the number of results you get from your vector search, isn't it? If you get only 3 results, you might miss. If you get only 100 results, you're quite likely going to get your goal set all in there, right? So you can increase K. But when you increase K and you feed all of that into the re-ranker, this is the gist of what they're trying to say, or the main point that they're making is this thing, that in the second phase, when you give it to the re-ranker, what happens is that when you're being sensible and you're using a reasonable amount of K, And somewhere in the paper, they mention that the K is 100. When you're talking of up to 100 documents being given to the re-ranker, it does a very good job. So let us look at this image a little bit more carefully. I will just blow it up. I hope I can. Look at this. In this, do you guys see this dotted line here? I'm putting out it in blue. This blue line, just to illustrate it, this is the result that you get, recall that you get from the retriever. So if you ask the retrieval, recall at top 10 results, doesn't matter if you ask the retrieval system to get anything more than 10, it will have the same ranking, isn't it? So its performance is not going to change as you, instead of 10, you ask it to get 100 or 1,000 or 10,000, isn't it? The only thing that will happen is the latency will increase because more data is being retrieved from the database, right? Searches are being done. Other than that, but in terms of AI, recall at 10 means in the top 10, how many of them were the belonging to the gold set, right? That will remain constant. Now, what you expect, look at the blue line, the black line here. This black is the expected. All of us have internalized that as we increase the number of results we get and we pass it through the re-ranker, the performance of this will get better and better and better, right? It will keep on improving, right? And ultimately, it will saturate near, the idea is that there should be a recall of practically 100%, right? It will be, one would imagine that what they're alluding to is a 1.0 recall, near perfect recall. It will saturate near perfect recall. Does that make sense, guys? Everything, pretty much all the top 10 results will belong to the goal set, right? In fact, your goal set will be there in all the, will be there. Yeah, go ahead.
What is recall at 10?
Recall at 10 means it's basically this. If you look at the top 10 results, right, how many of the real documents, what proportion of the real documents made it into the top 10? Okay? So in particular, if you have exactly 10 documents sitting there, real documents in your goal set, did all 10 populate the top 10 results? Are we together? And so what it means is, you would expect, this is what you want, that between the retriever and the re-ranker, the end result would be, you would get near perfection, right? Now, what happens, unfortunately, is what they point out in this thing. Look at what they do. They are saying what happens is, in reality, when you use a re-ranker, it goes up to a good value, but beyond a certain value, when you get more and more search results, your recall actually catastrophically falls, right? And the whole thing is, why does this happen? How can this happen? The whole assumption was re-rankers are even better, isn't it? They would sort through it and get it right. And that's the mystery. And we will discuss this mystery. Now, first of all, this paper is a very experimental paper. Most of it is in showing that this happens, right? And then a little bit of the paper goes into speculating why it happens. Why it happens is still an open area of research. The value of the paper is that it makes us aware that it does happen. Having said that, I must also say that if your K is in the order of 100, you don't need to worry. This problem won't show up at sensible values of K. It shows up for very large values of K, right? So in a way, you can say that this is of academic value because it's trying to point out the danger that in practice, don't do that. Don't go to very high values of K, but more from a theoretical perspective to make researchers speculate. Why does this happen? It goes against the grain of what you think would happen. Yeah? And why does it happen? So, all right, with that as a background, let's go and read this paper. The abstract says it all, and the rest of the paper I'll sort of jump through just through figures. It says re-rankers, typically cross-encoders, are often used to rescore the documents retrieved by cheaper initial IR systems. IR search engines are the retrievers, right? Why are they cheaper? They're computationally cheaper, right? This is because, though expensive, re-rankers are assumed to be more effective. We challenge this assumption by measuring re-ranker performance for full retrieval, not just rescoring first stage retrieval. So one of the things they do is they say, okay, suppose you didn't do the retriever at all, the vector embedding at all. Go back to 2018. All you had is the transformer itself, and you compared the query against all the documents, bizarre number of documents, 10,000 documents. Would you assume that that would produce better results than through retrieval, through embedding vector search? You would assume that because embedding vector search is an indirect approach. What they find quite remarkably, and this is a surprising thing, which they say in the next sentence, our experiments reveals a surprising trend. The best existing re-rankers provide diminishing returns when scoring progressively more documents and actually degrade beyond a certain limit. Not only do they degrade, they actually, ordinary retrievers, vector-based search begins to beat it completely. So that if you are retrieving a lot of documents, you actually shouldn't be using a re-ranker after that at all. This is a surprising finding. In fact, in this setting, re-rankers can frequently assign high scores to documents with no lexical or semantic overlap with the query. In other words, it will produce as high top search results, sometimes junk, right? Whereas a semantic search, a retrieval system would not do that. It would stay consistently. So it won't, in the best of case, it will not achieve the performance of a re-ranker, but its worst case is much better than the re-ranker's worst mistakes. Yeah? That's the point they're making. We hope that our findings will spur future research to improve re-ranking. So one of the observations they make in trying to interpret the result is they're saying people haven't paid attention to re-rankers and improved it. The embedders, encoders, text encoders have been increasing better and better. As you know, there is the MTEB leaderboard, right, in which people continuously monitor which encoder is better, right? And month after month, newer and newer encoder keeps coming up and gets tracked in the leaderboard. But re-rankers, apparently not enough effort has been given to really being serious about improving the situation with re-rankers. And I believe one reason is that re-rankers actually, for small k, for reasonable k that most of us use, they do very, very well, as we will see in the result. So this is actually dealing with the frontier where they have to re-rank a large number of documents. And what they're saying is perhaps it's time to make the re-rank, give another thought to re-rankers, make them better, because everything will improve. For big K as well as for small k, it will improve, right? Number of documents will improve. It goes on to say, so I'm going to miss all of that and talk about the paper mostly through the images. So let's look at figure 2. In some cases, when evaluating in a fair competition, ranking the full data sets, re-rankers are less accurate than retrievers. So this is it. Look at this. What you suppose, this dotted line is the performance of a retriever, right? That is a text encoder and then vector search, right? Now, that is the dotted line, this one. So what do you expect? You expect that when you bring in a re-ranker, the performance would be better, isn't it? Consistently better. What actually happens that if you do a competition between them, you will find that the re-rankers actually tend to underperform the retrievers. And that is the surprise. It doesn't always happen, but it happens in some situations. Now, the whole question is, so this now deals with what it is and what models they chose. The open, like for re-ranker, they chose these models. Now, by the way, BG also for encoding, as you know, are, if you look at dense encoding, text embedding, this is the OpenAI's closed one, but in the open source, okay, in the open source, the BGE is, BG large is considered to be a pretty good one. So they use a mix of open source and closed source vector encoding. The idea is to do a fair comparison between the best of both, retrievers as well as the re-rankers. They create two data sets, an academic data set and then an enterprise data set. Right? Enterprise means much more closer to practical real life examples. And now let's look at it through examples. What is it? Let's look at figure 3. Recall at 10 when re-ranking, averaged across academic data sets. The dashed line shows the first stage recall and the solid line is the re-rankers recall. So once again, when we look at the dotted line here, recall from the retriever will remain the same. It doesn't matter how many documents you have, right? Number of documents. It will keep getting you the same result. On the other hand, if you notice, by the way, BM25, when you use BM25, which is the here, BM25 binaries, then what you start observing is that based on the embedding models and the things that you use, you expect things to be, the oracle, by the way, is what you really want perfection to be. What in reality happens is it doesn't work like that. Do you notice that most of these, look at this one, for example, using the Voyager encoder. Voyager is an encoder, and then you apply a re-ranker. When you apply a re-ranker, let's take BGE re-ranker, right? Look at BGE re-ranker, it's the red line. So it is this line. Compare it to the not using it, just leaving the retrieval search results. Isn't it surprising that using a re-ranker actually screws it up? Are we seeing it, guys? When you use a re-ranker, your performance, your recall actually begins to precipitously fall. But beyond 100 documents, you start seeing a significantly poor results. And the same is true for the other encoder also. Now, this is true for academic data sets. It's even more true for enterprise data sets. Right? Now, with enterprise data sets, one of the interesting things you observe, by the way, when you, academic data set, by the way, I'm not going to consider, I shouldn't even have considered because they are doing some things very interesting. But let's look at the real life situation. What you do want is that recall should continuously go towards the oracle, is that it should go towards 1, right? When you use a plain text BM25 algorithm, so BM25 is used for what? Retrieval, means you're not doing vector search. You're just doing BM25. From the BM, like Elasticsearch. You know that Elasticsearch and all of this, the old traditional I mean, in a way, almost non-AI, but okay, let's give it with that. Those approaches, if they really need some transformer magic to be sprinkled in. So this thing, a re-ranker makes an improvement. Do you notice that all the re-rankers are improving the performance, right? Compared to the baseline. The baseline is what BM25 is giving you, the recall that BM25 is giving you, which is 50% recall. And so applying a re-ranker really makes sense. That is common sense. You would expect that. But what happens when you use a vector search, like a semantic search, right? Then what happens is, here is the baseline, and observe something very interesting. Up to 100, look at this line, up to 100, these re-rankers tend to bring about improvement, except for one. For some reason, that one doesn't seem to be. But beyond 100, do you notice that their performance begins to fall? Right? In fact, it falls beyond 1,000. They all begin to fall. They begin to be counterproductive. They actually worse. Right? So if you go and retrieve 1,000 search results and you feed it through a re-ranker, you're quite likely to have end result that is worse than what you expected. Right? Does that make sense? The same is true. So this is the main message they are giving out. And the other thing they are saying is re-ranking on the entire data set. Like what happens if you try to say, all right, let's go and let's look at the enterprise one, look at the recall and basically say, how does the recall improve? Recall at K, when you retrieve thousands and thousands of values. So let's look at the 100. At 100, you can see that BM25 is doing pretty badly. Any kind of a, if you just use a read anchor only means you have taken away the retriever. You're directly feeding it into the full-blown transformer. These things are doing better, right? And as you keep on doing it, they do improve. But look at something. The point that they're making is actually reality. Why is it that this happens? And so they have some surprising findings. Let's look at the finding. What happens? Suppose you have a query like this, which is from the bio data set which you put in the academic, sci-facts, scientific facts. Many proteins in human cells can be post-translationally modified at lysine residues via acetylation. I'm sure it means something to the biologist. I'm completely lost what it means, but it does mean something. So the positive document, you notice that retriever puts it at number 1. Reranker puts it at number 39. And here are the keywords. Protein, these things come up. Now comes the surprise, a bad result, a negative example. Look at this is a very interesting example of where the reranker gets it wrong. It brings in a piece of document which even as a non-biologist we can tell doesn't seem very relevant, but it is giving it a very high rank. You see, reranker is saying rank 5, but what did the vector search say? Vector search is saying, no, this is practically irrelevant, isn't it? This is a classic, this is a surprising evidence that sometimes bringing in reranker is actually counterproductive. Do you see that? And the whole question is, how in the world did that happen? A reranker is a direct comparison between two texts, whereas a retriever is using, even in the case of AI search, vector embeddings. It's a vector search, right? Semantic embedding using a transformer encoder and so forth. So how in the world is this happening? That is the mystery. And that is why I suppose it took so long, so many years for somebody to discover this, that this happens. Nobody assumed that it was happening, but it seems to be happening. Again, another example is the binding orientation. It's a science example and hard for me to tell, but the basic thing is that reranker puts it at number 2, whereas the retriever, plain old retriever, will say, no, this is a pretty irrelevant document.
But why it did it? I mean, that is not clear, right?
No, so we will come to the hypothesis on why it is happening. The hypothesis is pretty plausible. I'll come to it.
Okay.
Next is another example. This example, because it's not deeply biology, even I could understand. Or actually, it is bio, but still science. Less than 10% of Gabonese children with, well, I can't pronounce this thing, Schimmelpenning-Feuerstein-Minh syndrome, SFM, had a plasma lactose of more than 5 millimoles per liter. Now, positive document, the important thing is retriever said 5, reranker actually gave it a 33, which means that if you're looking for top 10 results, it wouldn't show up, isn't it? You would miss this document. And what instead the reranker brought forward, actually they forgot to put the numbers here, what the reranker brought forward as a high candidate is this one, which even we can tell is not relevant because it has to do with kitchen sink, a combination of sink and dishwashing apparatus having a sink sharing a common sidewall with a cabinet defines a closed space, right? Even as non-biologists, we know that this is really bad, isn't it? So I suppose they proved the point. The point they were making is, be careful. Don't just assume that rearankers always improve, isn't it? So, and in other words, use caution. You have a legit reason before you go to irrationally large document retrievals from the retriever and push it through the reranker. Yeah? Don't do that. Right? Now comes the question. They ask a very interesting question, which is that Is there a problem with the rerank? The way that we have implemented it, namely using the encoder part of the transformer, the BERT-like architectures. Is there really a problem with that? And one clue they get is they ask themselves, what if we used a LLM? By LLM these days, people often mean the decoder architecture, the decoder part of the transformer, right? What if we did that? Suppose you are allowed a large context window. I'll simplify. The page talks about, document talks about, this research paper talks about sliding window over lots of documents. I won't forget about the sliding window. Just imagine that you have very wide context length. And you could give all the documents in the context length and you could prompt. You say, if this is the query, you, the LLM, go re-rank or rank the order of the documents by relevance. You can give it to an LLM to do it, right? You can give it to GPT-4o, Cloud, Gemini, whatever it is, right? Llama, assuming a sufficiently large context window. When you do that, what are you giving? You're giving a list. And you're saying, giving this query, reorder the list by relevance. And you're asking the decoder architecture to do it, the LLM to do it. So the LLM, therefore, is acting as a prompt-based re-ranker, isn't it? It is acting as a prompt-based re-ranker. In that situation, look at this, something surprising comes up. This is the black line that comes out when you use a LLM-based re-ranker. And once again, this is your oracle. This is what you want to happen, right? The perfect situation. Now look at this. Do you observe that all the traditional re-rankers are underperforming? Do you see this, guys? All the traditional re-rankers are underperforming, right? They are in the underperforming regime. So what does it mean? The question is, are we getting a clue about what's happening? They have made very interesting points, but I'll try to simplify down of their hypothesis. So first thing is, it means that all is not well with the way we have created the re-rankers, isn't it? They were all encoder based, and now the question is, why is it that something LLMs are not trained to re-rank? I mean, they can do it. They're general purpose machines. But when a general purpose machine like a LLM, which has admittedly a better understanding of the language, is able to re-rank better than a dedicated fine-tuned re-ranker, then obviously you would agree that all is not well with the world. We need to fix things. So when you fix things, you have to first ask what went wrong. And so that is what the rest of the paper is about. They go and discuss it. And the whole question is, what are the reasons that this happened? So there are many hypotheses they come up with. The first thing they point out is that, see, the re-rankers at this moment have not been habitually trained with negative examples because they were trained to be re-rankers. So you would compare a query against results that are similar and you're trying to re-rank between them, right? So for example, if you're talking about, let us say, golden retrievers, in the document, in the test doc, in the data, what you would do is you would create pairs. Similar pairs would be something about dogs, maybe Labrador or something like that. You wouldn't take suddenly a statement from medical or bio or astronomy there, right? Or something like that. You have not, so there is basically an exposure bias. You have a very limited set of negatives during training. So basically what they're saying is, when you do this so-called point-wise re-ranking, this point versus that point, which should be closer, right? You're not that careful about your hard negative examples. And because people haven't been careful, they're paying the price. It's a hypothesis. It seems plausible. It is one reason that could be, but it is a reason, if this hypothesis is true, it admits a remediation, isn't it? Just go create better data sets, have a loss function that really pays attention to the negatives in the training, right? So it's a curable problem, what they are saying. And they explain this here. They say that it has to do with the fact that it has been expensive to do re-rank training. We talked about that re-ranking, when you train a full text versus text comparison, is expensive. So people don't create that many examples. Total data on which it has been trained is less. Look at this, right? So when you do the encoder training, you do lots of negatives. But when you do re-ranker training, you take only 4 randomly selected negatives. So the amount of training that it goes through in the cross attention is somewhat limited. The other is what they call re-ranking as ensembling. See, I will explain it slightly differently than the way they have written it. And I hope I nevertheless capture the same thing. See, let us say that there is a certain probability that the re-ranker makes an error in every comparison. Let's say that that probability is fixed, right? Let's say that there is a, see, this is my way of simplifying what they are trying to say here. I'll simplify it a little bit. Let's say the probability of every comparison, of error of every comparison is epsilon, right? So what is this error? That 2 documents, the query and an irrelevant document, random document, is being marked as very similar. That's an error, isn't it? That represents an error. Let's say that that error has an epsilon chance, right? Now you realize, so let's say that your re-ranker is 99.9% accurate. Only in 1 in 1,000 cases, it will make a mistake, right? Or just to simplify, let's say that it's 99% accurate. One out of 100, it will make an error. Now what happens when you shove 1,000 documents through it? It will make at least 10 errors, more or less. Expectation value of errors is about 10, right? And those errors, basically your top 10 results will be filled with, or will have quite a healthy mistake sitting there from the re-ranker, isn't it? Because it is re-ranking 10,000 documents. It has made mistakes. And so a lot of the mistakes are bubbled to the top. Right. So Chandra, I hope that gives you some clue into this weird case. Right. That is again an intuition that they bring. And the third thing that they do is they say that, see, fundamentally, right, when you do deep learning, there is a certain robustness issue. Now, this goes to deeper issues with deep learning algorithms, neural network algorithms itself. As you probably know, we did, those of you who have been part of support vectors know, that we did, when we do AI and security, we talk about this famous case that you can show it an animal. What was it? A panda. This was the work of Ian Goodfellow, I believe, and others in the original paper. You have a panda, but you make imperceptible perturbations to the image. And then the deep learning neural network will now recognize this not as a panda, but as a gibbon. Right? So there is inherently hackable aspect to the, or sort of lack of robustness to the deep learning algorithm. This is something that people have observed with deep learning. And people have observed that predictions change if you just substitute a word by its synonym. Similarity between two things will re-ranker, especially when you do direct text-to-text comparison. Then, if you substitute a word by its synonym, surprisingly, the similarity score changes. Now, one interesting thing that I found, actually, I've observed this myself. Interesting thing is that the vector approach, the retriever approach, first going to a vector embedding and then comparing the vector, I have found that that is actually robust against it, much more robust. But a direct text-to-text comparison is a little bit more vulnerable than the indirect approach to go through vector search. So anyway, that speaks to the fact that deep learning itself has a robustness problem. So, and then there is a whole thing called reward hacking and so forth. So what happens is that you give it one goal, but it actually finds some other goal to optimize, right? It finds a shortcut. Yeah. And things like this happen. These have been studied. I won't go into that. So that is one aspect. The next aspect that they point out is, see, when we do, let's say triplet loss, any one of these things, we are trying to say this item and those items are similar, bring them close. But and the third item is not similar, keep it far. Right? Even when we generate using n pair loss, you take two similar, and then the third you keep picking from other items in the mini batch. Yeah? Nevertheless, it's a point-wise comparison. We never really train the encoder to do the work that it is supposed to, namely, given a list, re-rank the list itself. A loss function that literally penalizes you in getting the order of the list wrong. We don't do that. So this points out that maybe we need a better loss function that is much more centered around list-wise comparison rather than point-wise comparison, right? That is the other. Lastly, they say that, see, and the many, see, these are hypotheses. Can we do better fine-tuning, or is fine-tuning itself a problem? Now, this is again one of those hypotheses. See, you can bring in, I don't know whether it necessarily is the cause. I don't think this is the cause, but the authors certainly posit that it could be. One problem with re-ranking has always been, not fine-tuning. Fine-tuning a model always is of catastrophic forgetting. So what they are saying is that when you fine-tune a model to become a re-ranker, which is the usual way you produce a re-ranker, maybe it is becoming good with re-ranking on your training and test data, but in the process it's losing its general ability to understand language itself. So there's some level of catastrophic forgetting. Otherwise, how would you explain the fact that a decoder-only model, a LLM, outperforms the encoder, a fine-tuned encoder? A general purpose LLM outperforms a fine-tuned encoder, a re-ranker, right? That seems paradoxical. And so one possible hypothesis is that in the fine-tuned re-ranker, there has been some effect of that dreaded beast of fine-tuning, namely catastrophic forgetting. Right? So these are different ways or hypotheses that they bring to the table. And that was this particular paper reading. I invite you to read this. It's always a delight to read a paper that breaks your underlying assumption, because we all build our RAG and our search architectures always in two stages, a retriever followed by a re-ranker. Now, what are the practical takeaways from this paper? The practical takeaways is, be very careful if you're taking in of shoving more than 100 documents for a query to compare against. Right? And in some sense, it's sort of like the diffusion of errors. For me, the most plausible of the hypothesis was what I would call the diffusion of error hypothesis. If there is an epsilon probability that the re-ranker will make a mistake, the more documents you feed through it, the higher the probability that mistakes have happened, and those mistakes will bubble to the top, right? And therefore, do not shove too many documents through the re-ranker. Yeah. That seems to be the takeaway message until people find a way to improve the re-ranker and solve the problem. But in today's world, in practical projects, that is a caution worth exercising in your RAG and in your search architectures that you're implementing. So that's that, guys. Any questions, any comments, or anybody would like to suggest a hypothesis or a variation?
So one thing in my head is, why don't we just use an LLM for the re-ranking bit of vector search?
That's a very good question, and the answer to that is a very good question. Actually, in view of this, you would be tempted to say, let's start using a LLM. One aspect with the LLM is the latency. LLMs are computationally more expensive, and because they are per token generative engines, right? Remember, they're generative engines. You are now limited by token count. If you ask it to re-rank 100 documents, each document has, let's say, 100 tokens. Yet you're producing 10,000 tokens just in the reordering of them, right? And generally, decoders or re-rankers LLMs are computationally hand-waving argument, I would say at least an order of magnitude more expensive and higher latency than re-rankers and encoders, retrievers, because they are both encoder-based models. Encoder-based models are smaller, they're computationally cheaper, they have lower latency.
Have these people done comparison with Colbert?
That is
For
a very
the-
good question. In fact, that was a question I had in mind. They don't mention Colbert, but see, they already say that re-ranker, even a standard retriever, beats a re-ranker hands down beyond a certain number of documents. So one would assume that Colbert will blow it out of the water even more, isn't it? When you go to
Yeah.
Colbert, Colbert will do even better as a
I mean,
retriever.
Colbert is closer to a re-ranker than a
Yes,
regular, no?
absolutely. The right question to ask is, has anybody used Colbert as a re-ranker? Right? Because Colbert doesn't do string to string comparison. Chandra, if you remember, right? A Colbert is just multi-vector comparison. And therefore, one immediate question to ask is, why not just use Colbert as a re-ranker? Because
In
it is
fact, I was reading yesterday in Qdrant, they are actually suggesting to use Colbert as the re-ranker because of the faster performance than a regular re-ranker.
absolutely. Yeah, and I completely agree. Not only is that, in my experience, actually, you can remove the two-stage process altogether, because if you look at the Colbert, actually people write it Colbert, but they pronounced it as Colbert. If you look at the Colbert paper itself, there is, yes, it makes sense to do a cheaper single vector, like, retrieval, and then
No,
do
they actually in Qdrant, they are suggesting do the bi-encoder first, and then because whatever it
I'm
is,
getting,
Colbert
that's what I'm saying.
is slightly more computation.
Yeah, that's what I'm saying. The
Okay.
traditional, what Qdrant is suggesting, I know what they're suggesting. They're traditional thing. They're saying just do a single vector comparison for retrieval, right? ANN.
Yeah.
And then do the late interaction binding Colbert for real.
Yeah. Correct.
What I'm saying is something different. I'm saying that, in my opinion, unless your document size is humongous, like, so for example, as in here it's support vectors, right? We have all our lectures converted to text. Why even bother? When your corpus size is small, just do a one, like see, people use the word single vector search, multi-vector search, or late interaction. Just stick to one. Just directly do Colbert. Just directly do Colbert. Forget about doing a single vector search before that at all. Just use Colbert as your retriever and re-ranker all in one.
Okay.
Now, what are the costs associated with that? The cost is storage. There's a compute cost, but there is also a storage cost, because now you're storing not one per document. You're not storing one vector, or rather one chunk. You're not storing one vector. You're storing n vectors. Which has been the problem with Colbert, which is why people have been hesitant in using the late interaction. But my own feeling is, as you know, and I've mentioned this many, many times, I have a very strong preference for Colbert and Colpali.
Okay.
So that is a follow-up study, actually. Maybe we can do that, and we can post the results. We should certainly try that, because they have made the data sets available on which they did their study, as far as I know. We should probably try this experiment out and see what happens. Anything else, guys? Anybody else has a comment? We are very quiet today. The year has started very, very quietly. I'm looking at chat also. I don't see any comments. Okay. All right, guys. So if there are no other thoughts, anything else? Chandra, any other thought? Anybody else?
No, nothing from me.
So if there are no other, Prasanna, anything else?
No, I asked the question.
That's it. Yeah. All right, guys. So thank you for being part of our support vectors AI learning community. Thanks for being part of our meetup. I look forward to seeing you next time. Actually, next week we have a very interesting paper, and it will be Sushinda who will be presenting it. It is about XNet, or using the Cauchy function as an activation function. There's a new learnable activation function. It's a new kid on the block, and Sushinda has actually written code to demonstrate how well it learns, how fast it learns. It's amazing, actually. So the next two talks will be from Sushinder. He'll talk about the XNet research paper, and the week after that, he will talk about the state space model, the S4 and Mamba. So two really interesting research paper readings coming on the horizon. I have to update the meetup. Those are the two readings that are coming, and Sushinda will be doing that.